This is the answer guide video for ELR 3.4 on the Unit 3 study guide. For 3.4, we're going to be doing some calculations for mass and weight on other planets. The biggest thing that you should know about this one is that we're really not doing anything different than we've done in the past. We're still doing this F equals ma equation, Newton's second law. In fact, when we say weight, weight is a force. And if you are going to be doing any kind of calculations, all of your weight units are going to be in newtons. So nothing much is different here. One thing that you do need to be careful about, though, is that all of your masses need to be in kilograms. And so I will throw you some curveballs on the test. Make sure that you're checking some units. In fact, this might not be a bad idea to put on your note card to remind yourself. So for number one, force of gravity on Earth's surface for each of the following masses. So force of gravity on Earth is because of the acceleration of gravity, and acceleration of gravity on Earth is of course 10 when we round it, so that's what we're going to be using here. So for 75 kilograms, we are in the right unit. We're going to be using F equals ma, and when we substitute in, we're solving for force. Our mass is 75, acceleration of gravity is 10, so we end up with the number 750. Don't forget your units, newtons. For the next one, we've got 454 grams. Before we can do the math on this one, we've got to do some converting. So 454 grams, there are 1,000 grams in a kilogram, so we've got to go 3 to the left. That's going to be the same as 0.454 kilograms. Now we can do our F equals ma. And when we substitute in, we're going to get force is equal to 0.454. That's our mass. Acceleration of gravity is 10. And when we solve that, we're going to get 4.54 newtons. For number two, Emma is an astronaut who has traveled to Mars. While there, she found that Ralphie the rock accelerates at 3.6 meters per second. So I'm going to pause right here and point out how, remember when we did the feather and the bowling ball, that when something accelerates on Earth, it doesn't matter what it is as long as air friction is being taken out of the equation. Everything accelerates at the same rate. So when she's on Mars, this is the acceleration on Mars, 3.6. That means that everything accelerates at that rate on Mars. So we keep going. She also finds that on a Newton scale, when she steps on the scale, it reads out 180 for her. So the first part of this question is saying, what is her mass? Well, like in the other parts, we're going to be using Newton's second law. For the first part, or for the substituting, I mean, we're going to be plugging in for force what her scale reading was, 180. So her force is 180. We don't know her mass, that's what we're solving for. And we were just told that the acceleration on this planet is 3.6. So 3.6. Now we just divide both sides by 3.6, and we're going to get her mass, which works out to 50 kilograms. For letter B, it says, what would the Newton scale read if she stepped on it on Earth? So this time we're going to a different planet that has a different acceleration. So this time acceleration is 10 meters per second squared. But the thing is that mass doesn't change. Your mass doesn't change just because you left and went to a different planet. Mass stays the same no matter where you are. So when we plug this into the new equation, we're going to still be using Newton's second law. We're solving for force. Her mass hasn't changed. It's 50. She's just on a different planet now. And this planet has an acceleration of 10. So if she steps on a scale on Earth, it should read 500 newtons. So the same person that steps on a scale on Mars would have a scale reading of 180. That same person would have a scale reading of 500 on this planet. For number three, we're dealing with a serious jar of pickles. So number three says, what is the mass of a jar of pickles that is pulled down by the force of gravity of 167 newtons on Earth's surface? So for this one, we're still using F equals ma, Newton's second law. And we're given a force, and we're told that it's on Earth. We have all the pieces of information we need. So the force is 167 newtons. That's the weight of the pickle jar. And we're trying to solve for the mass, and this is on Earth, so acceleration is going to be 10. So we do 167 divided by 10. We're going to get a 16.7 kilogram, don't forget that this is in kilograms, jar of pickles. For number four, which two quantities are measured in the same units? Let's look at one at a time. Velocity is meters per second, acceleration is meters per second. Those are not the same unit. Weight is measured in newtons, so is force, so there's our answer, but let's just check the rest. Mass is measured in grams. Weight is measured in newtons, like we just said, so those aren't the same. I should have done that too. Meters per second and meters per second. That's why those weren't correct. And for D, force is measured in newtons. Mass is measured in grams. So D is not correct either. B is our answer. For the last part, we are being asked to do some calculations for different planets given a person's mass. So we're told that the mass of this person is 103, and it wants to know all this stuff about Earth, Mars, and Jupiter. I'm going to tell you that 3 of these boxes are sort of trick questions. Maybe they're tricky just because they're so easy. But a lot of people fall into this trap. They think that, oh, just because I went to a different planet, I all of a sudden have a different mass. Not true. So these ones where it says, what is her mass on Earth? Well, it told us that, 103. The next one, what is her mass on Mars? Well, just because you went to Mars, your mass didn't change, 103 grams. What's your mass on Jupiter? You're still the same person, 103 grams. Think of mass as like a measure of how much stuff you are. Well, you don't change how much stuff you are just because you went somewhere else. How hard it gets pulled down into that planet might be different, but that's weight. So let's do those. On Earth, we're going to be multiplying by 10. On Mars, it looks like we're multiplying by 3.8. And on Jupiter, we're multiplying by 26.6. So Jupiter is a very large planet. It's going to have much more acceleration due to gravity. Once we plug these into a calculator, we're going to get 1,030 newtons for Earth. For Mars, we're going to get 319.4 newtons. And on Jupiter, 2,739.8 newtons.